Thank you.
Okay, thank you very much, Dr. McKnight and Dr. Hu. So I'm going to introduce our next speaker, who is Dr. Stefan Scharring from the University of Freiburg, in which he got a degree in physics in 2000. From the University of Stuttgart, he received his PhD degree also in aerospace engineering in 2013 for his thesis on laser thermal propulsion. Dr. Scharring works as a laser scientist at DLR today in the field of numerical modeling, and his expertise comprises numerical simulations on laser-matter interaction and fields of laser propulsion and space debris remediation. Moreover, laser safety aspects, as well as weather analysis for outdoor laser operations, have been part of his expertise in recent studies. So he is going to talk today about passive optical observation to high power laser irradiation. And Stefan, the floor is yours.
Thank you so much for this kind introduction. So you can see my slides and can hear me? Okay, I guess it's like that. So welcome everybody to my talk. On behalf of our space debris team, I would like to give you an overview about our activities in the field of space debris, covering various aspects from detection to debris mitigation. Our team is located in Stuttgart, which is in the south of Germany. And we are here at the Institute of Technical Physics, which is a part of the German Aerospace Center. Well, just to introduce our institute, the Institute of Technical Physics focuses on research and development of laser applications in various DLR domains, not only space, but we as well have aviation, where we develop optical sensors for flight instrumentation, dealing with innovative measurement technologies, for instance, like turbulence detection. And beyond that, we also undertake research in the field of security and defense, ranging from remote detection of dangerous substances, chemical, biological explosives, to long-range laser effectors for air defense or other applications where we make use of directed energy transmission. But these are different areas, and for this talk, I come to space and in particular space situational awareness. And just as a brief motivation, but you have already 1 hour motivation, just briefly, I want to refer to the well-known collision between Cosmos and Iridium about 15 years ago. And what I want to point to is that this event generated more than 2,000 trackable debris pieces, and each one of them is in principle capable to destroy just another satellite. And this even years after the collision, as you can see on the right of this image. And the point is that the predicted miss distance there was around 600 meters. And so I think this illustrates the need for research and development in the field of space situational awareness. Basically, there are 2 different quantities which have rapidly grown in the orbital environment, as you have already heard from Darren's talk. Firstly, the number of launched payloads, and secondly, the number of space debris objects. Together, these increasing numbers put a large pressure on space traffic management. And I think it's important to be aware that even very small space debris still matters, because there are very high kinetic energies. And you can expect satellite damage from debris in the size range of 1 to 10 millimeters. Debris between 1 and 10 centimeters can terminate even a satellite's mission. And finally, there are lots of large objects, which we have just seen, which can cause catastrophic collisions that pollute the entire space environment. And taking these estimates from modeling on the small debris, one can state that less than 4% of all debris targets greater than 1 centimeter are already been cataloged, and the rest is silent dark numbers where you don't see it coming, what can even be lethal for your satellite. So finally, debris generation has developed its own dynamics. The number of small debris is predicted to increase strongly, even if no further launches were undertaken in the future, as we can see here on the right in the graphics from ESA. So the diagram suggests that we have a sort of disaster in slow motion. And some researchers state that what we call the Kessler Syndrome has already started at certain LEO altitudes. So for our work, this means that we have 2 different objectives. The first objective is to protect operational satellites. and the second objective, to protect the orbital environment itself. And regarding satellite protection, our institute's mission covers laser optical technology for precise space situational awareness, since currently a lot of collision warnings for operational satellites are raised, while only a few of them are very critical. And the idea is that with our passive optical sensors, space debris objects can be tracked, and the related data serves as target acquisition for subsequent laser tracking and ranging, which allows for high precision orbit prediction. And as these measurements have a limited range around the laser station, we are working as well on geographically widespread sensor networks. Beyond the protection of operational satellites, the orbital environment itself has to be protected. And first of all, as we have already heard, this comprises rules for removing satellites when their mission is finished. But for space debris that we already have, first removal missions are planned, for example, for ESA, JAXA, and the UK. And towards the end of my presentation, I want to give you an outlook on how our conceptual work could contribute in this field. Finally, there are some very basic measures for sustainability, like discharging batteries, handling residual propellant, and of course, abstaining from anti-satellite missile tests. So this is the outline of our research. The foundation of our work are laser optical technologies comprising detection, tracking, and ranging of satellites. We'll go then to space debris detection and tracking, which leads us to orbit prediction and surveillance networks. And finally, we come to space sustainability, which covers innovations for space traffic management, attitude estimation, and laser momentum transfer. And just here, I want to acknowledge all my co-authors who have provided me with their input to each one of these sections. Okay, so first of them is my colleague Ranka Rosak, who engages in passive optical detection of space objects. And passive optical staring basically means staring at the sky in the twilight. And at that time, we already have a dark sky background while the objects in orbit are still illuminated by the sun, and so they can be detected. And you can see this in this long exposure photograph on the left. We have the stars as point sources, while the detected LEO satellite leaves a streak inside the field of view due to its motion. And from this observation, we can use the stars as calibration points for azimuth and elevation data. And with this, we can determine the angular motion of the satellite. Together with the timestamp of the recording, we obtain initial orbital data, which gives us a so-called tracking data message that can be handed over to a ranging system. And the great advantage here of staring operations is that we don't need any initial information for detection, but we simply have the streak on the photograph and that's it. So this allows for the detection of untracked space debris, which is extremely useful since, as we have seen, the vast majority of lethal debris is still undiscovered. So typically around 500 objects are detected per night in our observations. Our system is called Apparillo, which is an acronym for Autonomous Passive Optical Staring of LEO Flying Objects. The instrument comprises a sensitive high-resolution camera together with a wide-angle lens. At present, this yields a detection limit below 1 square meter optical cross-section. And the positional accuracy of our measurements is better than 100 meters. The Apparillo is a transportable device for autonomous operations, and its mass is just around 200 kilograms. Currently, we have a very small nationwide Apparillo network comprising 3 systems. And one advantage here of using multiple sensor locations in a network is that one can gain a bit in independency from adverse weather conditions. And of course, the sky coverage increases with every station that's added to the network, unless we use another benefit of multi-sensor observations. And this is when 2 sensors at different sites record the same object simultaneously, which allows us to have much better data precision because of triangulation methods. When data on angular motion is brought together with distance information, we obtain the full data which is required for orbit determination. And in this field, my colleague Felicitas works on a very compact device for laser ranging. In laser ranging, very short laser pulses are sent from a ground station to a target during its overpass. And some of those laser photons are reflected up there and can be detected on ground. And so from the time span between the outgoing laser pulse and the incoming photons, we can simply compute from the light speed the distance between laser station and the space object. And here, the mini SLR ranging system is a very compact, low-cost device, which is transportable and can be operated both autonomously and remotely. It's dedicated to ranging to satellites, which are equipped with a corner cube reflector that allows for retroreflection. And you surely know retroreflectors, for example, from your bicycle around construction areas or traffic signs. Wherever the light comes from, it will be reflected into exactly the opposite direction. So this highlights an object in the dark when you shed a light upon it. So this optical mechanism enables us to have a very high measurement range, up to 25,000 kilometers, even though the average laser power is only 4 watts, which is rather low. And moreover, with a pulse duration of 400 picoseconds, the emitted laser pulses are so short that we obtain a sub-centimeter data resolution in ranging. And as an example from our measurements of the mini-SLR, you can see a data plot from an overpass of the Legios-1 satellite, which is at approximately 6,000 kilometers altitude. And each point on the scatter plot represents a photon detection. So you can see here some background noise from atmospheric scatter all over the plot, but as well a clearly pronounced line where many photons are recorded. And this line gives a comparison between the actually measured distance and the range that was expected from orbit prediction before our measurement. And in this graphic, this means that the photons arrive between 15 or 25 nanoseconds later than expected. And in turn, this means that the orbital data should be corrected by effectively a distance of 2 up to 4 meters. So for keeping high precision orbital data up to date, there's a globally distributed network of laser stations, the so-called International Laser Ranging Service. And within this network, we operate the Mini-SLR as an engineering station, which comprises data uploads from our station. And since our device is very compact and cost-efficient, we think that the Mini-SLR bears the potential to greatly extend and unload this ILS network. So space debris usually comes without any retroreflectors, so it's not cooperative for laser ranging. So now we have to turn up the laser power and enlarge the receiver to collect more photons from above if we want to tackle space debris. And so this is the mission of the Orbital Photonics Group led by Gers Wagner. And 2 years ago, we have commissioned this Johannes Kepler Observatory in Empfing, which is a little village in the Black Forest in the vicinity of Stuttgart. And with a primary mirror diameter of 175 centimeters, this telescope is the largest space debris research observatory in Europe. The telescope is placed on top of a 15 meters high tower inside a rotatable dome. And our overall objective here is to detect and track space debris down to a size of 10 centimeters. As a very first step, passive optical tracking of CubeSats has already been demonstrated. Beyond that, the unique specifications of this observatory allow us to go much more into detail with our observations. The great amount of photons that can be collected during passive optical observations enables to have a high temporal resolution of the recorded sunlight reflections. And with that, the rotational motion and in particular possible tumbling of the debris can be deduced from intensity changes by light curve analysis, which helps to plan in-orbit missions like servicing or deorbiting. The large amount of received photons also opens up the possibility for spectral analysis of the debris reflections. From this, conclusions on the debris material can be made, which could be important for advanced concepts like debris recycling or laser-based removal. So in this regard, the Johannes Kepler Observatory serves as a research facility to characterize objects in LEO. For debris ranging, we operate a near-infrared near-dim YAG laser with pulses in the picosecond range, which gives a very good ranging precision. Currently, a laser of approximately 20 watts is employed, and of course, appropriate measures for laser safety are applied, among them continuous aircraft detection to avoid accidental eliminations. But nevertheless, we strive to explore the so-called eye-safe laser ranging. And for this purpose, a significantly larger wavelength of around 1600 nanometers will be used. And at this wavelength, the laser light could, in a very unlikely case of an accident, not travel through the human eye and therefore would not be focused onto the retina. So at such a wavelength, the laser power would not be dangerous for the human eye, as long as it's not intensified by using, for example, binoculars for observation. So coming back now to space sustainability, laser tracking data should serve for collision avoidance in principle. But what does this exactly mean? My colleague Jens Rothman works in the field of orbit prediction. And from his studies, we can learn something more about the usage of laser tracking data. When orbital data is measured, we have certain limitations regarding our predictions of the future trajectory of the observed object. First of all, we may have timing errors and measurement uncertainties that come with the technology which we use. But there's also uncertainty in the orbital environment itself, since the solar activity has a strong impact on the density of the residual atmosphere in space and therefore on the object's drag and velocity. So we can associate a space object with a so-called covariance ellipsoid, which quantifies the uncertainty of position and velocity with respect to all directions: direction of flight, radial towards Earth's center, and finally crosstack. So the scope of laser tracking and ranging now is to make this uncertainty ellipsoid as small as possible, at least much smaller than it can be done with radar systems currently. So generally speaking, laser tracking and ranging has to be undertaken again and again to assure a constant high quality of prediction, since orbital data gets worse due to this atmospheric effects. And you can see here from the graph at the right that with each measurement that the uncertainty goes down instantaneously, but then again grows constantly. Therefore, a widespread laser station network is required to provide frequent access to observations. But however, clear sky is required for observation, which is not always the case, as you can see in the graph at the large gaps where the uncertainty goes over the top. So therefore, a straightforward solution is to increase the number of stations. So what you see here is a 5-station network, and these are the results for a 10-station network. And you see less data gaps, better precision. Of course, the geographical distribution of the stations has got a large impact here, in particular regarding the local weather conditions. Moreover, orbital parameters have a strong impact on the revisit rate of a space object over a given geographical position. Eventually, and you might recall our initial slide from the Iridium-Cosmos collision, laser measurements have the potential to enable better orbit prediction for reliable assessment of the mist distance in a close approach. And in a study for ESA, we summarized that already a small laser station network, as you see it here, would reduce the number of false collision warnings by more than 90%. So how can we make space a better place? Well, everything starts with cooperation. And my colleague Niels Bartels, leader of Sustainable Space Photonics Group, works on innovative concepts to make satellites more cooperative. And this is how it looks. So you know that retroreflectors reflect the incoming light directly back to its origin. Our innovative concept of smart retroreflectors, however, even allows for satellite identification, just like the license plate on your car. So the simple technology relies on light polarization and works with a set of very small, lightweight retroreflectors, which can easily be implemented into satellites at low cost. In front of each reflector, there are 2 polarization windows, for example, a quarter wave plate or wire grid polarizer. And the angular orientation of both components relatively to each other effectuates a certain rotation of the optical axis when polarized light is transmitted through the polarization assembly. And so this rotation angle can be adjusted specifically for each one of these retroreflectors, and that's it. But this means it's possible to encode a satellite-specific identification number into the smart retro assembly. So these specific identification angles can be read out by laser ranging when we use a polarization generator for the laser and a polarization analyzer for the receiving unit. And within a few milliseconds, different combinations of polarizer and analyzer state can be probed. From that, one can derive the retro-specific rotation angle. And moreover, since we have a ranging precision in the millimeters range, it's possible to discriminate between up to 7 smart retroreflectors and their specific identification angles within a small smart retro assembly. And as our institute has a great heritage in the field of optic space qualification, we are pretty confident to introduce this concept soon for long-term operation in orbit. And such a tagging technology would be a great help, in particular for CubeSats, where frequently a certain fraction of them remains unidentified and cannot be registered for space traffic management. Using smart retros, satellite registration could then be completed easily. On top of that, with the help of laser ranging, orbital data would be significantly more accurate than ever before, which greatly helps to issue reliable collision warnings for space traffic management. Efforts for long-term space sustainability demand for in-orbit missions, for example, servicing operations or the deorbit of large objects. Rendezvous maneuvers, which with a tumbling satellite, however, are very complicated. And so the very first step in such an endeavor is rotation analysis. My colleague Tristan Meyer is engaging in the development of methods for analyzing rotational states from observations on ground. And the starting point for rotation analysis are light curves, which are the temporal intensity evolution of sunlight reflections from the object. Together with knowledge about the object geometry and its surface materials, one can start then to set up a model about how such a light curve should look like for different rotation velocities and spin axis orientations during an observation from ground. And our institute, we have developed our own software for modeling such light curves. The simulation tool considers the orbit geometry, the sun spectrum, as well as a three-dimensional model of the space object, including material reflectance properties. With that, we go into a ray tracing rendering engine, send the graphical output through an atmospheric transmission model, and then integrate the whole image so that at the end we have a single intensity signal which can spectrally be resolved. So doing this for each and every point in time of the observation period, we finally obtain a simulated light curve, which you can see at the end of our simulation pipeline. And obviously, simulation and measurement typically do not match right from the start, as you can, when you compare measurement with simulation here in the lower left. Instead, a multitude of combinations of rotational period, spin axis orientation exists, not to mention the many possible fine-tuning issues regarding the shape and material composition in the underlying 3D object model. Therefore, very sophisticated methods have to be applied in order to estimate the object's rotational state and to eventually assess the feasibility of robotic capture in space, be it for on-orbit servicing, recycling, or a deorbiting mission. So finally, we come to laser-based momentum transfer, which is my personal field of expertise. And in principle, laser momentum transfer allows us to change a debris trajectory by using a high-power laser from ground or far remote from space. And when using short laser pulses at high fluences, it is possible to vaporize a very thin layer of an object's surface immediately within nanoseconds. And the energy that is deposited in this submicron layer is so high that the vaporized material forms a high-speed gas jet with particle velocities in the order of several kilometers per second. And in turn, since we have momentum conservation, we observe recoil that is imparted to the target. This gives us a method at hand to change the velocity of an object in space remotely from ground. And so in this video recording, you can see an experiment with different centimeter-sized targets in vacuum. We have dropped them inside a vacuum chamber, and at a particular moment, they are hit by a single laser pulse. And you can easily observe how the trajectory of each object is changed due to the laser pulse. So with laser surface ablation, momentum coupling is rather large, giving us velocity changes of up to 1 meter per second and more in this experiment. But even without any surface ablation, there will still be momentum anytime, namely generated by photon pressure. So laser force coupling only by photon pressure without any ablation is rather weak, around 5 nanonewtons per watt. But we have been able to measure it using a sensitive torsional balance and a high power laser in the kilowatt range. And with this, we come to collision avoidance. Because using laser momentum transfer, it could be feasible to avoid collisions of space debris remotely from ground. And in particular, when both objects are space debris, and it's impossible to command a collision maneuver, then it could be possible to do this from ground and to apply laser momentum transfer to modify the debris velocity so that we have a safe separation distance between both objects. And we have studied this concept for the European Space Agency considering photon pressure and concluded that a collision avoidance would be feasible for small space debris when one would employ a network of 10 laser stations at 40 kilowatt power each. And you can simply buy this, so this is not unrealistic. With laser ablation, this result could already be achieved using only a single pulse at a multi-kilojoules energy level with a single station. The problem is that such lasers are not commercially available, and only a few of them exist in the world at dedicated research facilities. So meanwhile, there are several modeling tools at our institute which allow to project this concept deeply further into the future. And we find that in principle, it should be possible to even deorbit space debris in the long run by using high power lasers with several hundred pulses per overpass. However, there are some great technological challenges until such a concept could be implemented. But in principle, we think this could be an option for the future. So I hope that I've provided you with an insight about laser technology for space sustainability. Summarizing our work, we focus on object detection and ranging technology in order to acquire orbital data. And these technologies can be employed for operational safety using debris detection and ranging in order to improve orbit predictions. Beyond that, we support space sustainability in the fields of space traffic management, in-orbit servicing, debris removal, and laser-based collision avoidance. And in terms of sustainability, we work in 4 complementary directions. We adapt our awareness to the aggravating space debris situation. We try to avoid further collisions in space, try to delay the Kessler Syndrome by contributing to debris removal, and eventually transform the orbital situation regarding space traffic management and large-scale removal of space debris. And from my viewpoint, worldwide connections and integrated actions will finally make the real difference for system transformations. And in that regard, I'm very happy to being part of this workshop. And yes, thank you for your kind attention.
Okay, thank you, Stefan, for your very inspiring talk with covering a lot of topics. And we have time for just 2 questions that we have on the chat. So there are 2 very close oriented questions, and it's about why do you use satellite laser ranging instead of synthetic aperture radars?
Well, basically, it's the technological field of expertise that we have. The idea is that we have very low-cost devices, which are very flexible. And satellite laser ranging is particularly dedicated to geodesy satellites or science missions where we need a very high precision. And for this purpose, within this network, the ILS network, it's a very, very straightforward approach with a very simple station. Yes.
Okay, thank you. And the other question is from someone in the audience, reminding about one event that would have happened there in 2001, which is a collision between Cosmos 2221 and one NASA satellite. And the question is about the accuracy of the detectors and of the collisions. And I would add that, I mean, how much time can you advance or can you provide advance for a collision avoidance maneuver?
Well, the point is, you have seen this sawtooth-like, sawtooth-shaped curve of uncertainty. The point is that this uncertainty steadily grows. And so when we think of laser ranging, we have to think about when can we still acquire such a target to measure it anew and to bring the uncertainty down. And we found that, well, the time of so the data has a sort of expiry date of, say, half a day or a day, and so you have to continuously keep on tracking, and for collision avoidance, you still have those uncertainties which are left. And basically in our study, we thought that we have a 2-day time interval where we think, do we have to act? Do we start collision avoidance with lasers? But there's still some uncertainty left. So it's really a trade-off of resources, I think.
Okay, thank you very much, Professor Scharring. And we're moving to the next speaker. Thank you again.